This video explores random walks with memory. This type of stochastic process is sometimes called an elephant random walk, assuming that elephants have perfect memory. As regular viewers will know, I have a strong interest in Financial Times series. In previous videos, we covered random walks and the simulation of share prices. The stochastic processes we used are Markovian. This means that after observing today's share price, say PT, I know everything I need to know about the future. Share prices are fully revealing. This works very well, assuming that the efficient market hypothesis holds. However, there have been empirical tests focused on long horizon stock returns since the 1980s. Evidence suggests that long-range dependence can be observed. Yet measurement problems can make this assessment quite challenging. If you want to dive into this literature, I suggest to read pages 59 to 62 in Campbell-Lowe-McKinley, The Econometrics of Financial Markets. I discussed this classic book in a previous video. The finance and econometrics literature tends to focus on fractionally different time series to capture the alleged long-range dependence. You see an example on this slide. Note that capital L refers to the lag operator. So if you take the parameter value d equal to 1, you obtain the random walk model. But d does not have to be an integer. Hence we call this time series fractionally differenced. There is another way to obtain long-range dependence using random walks with memory. I refer to Schuetz and Trimper 2004 and an extension by Kumar, Harbola and Lindenberg 2010, which I cover in another video in more detail. The most exciting observation is that many phenomena can originate from random walks with memory. For instance, anomalous transport. Again, this is a term used in physics. It means that the stochastic process has a variance that does not increase linearly with time. Examples include jumps in a time series or periods with no activity. Let's have a look at these funny random walks proposed by Schuetz and Trimper's 2004 paper published in Physical Review E. Now there is a stochastic evolution equation xt plus 1 equal to xt plus sigma t plus 1. This refers to a one-dimensional random walk. The random variable sigma t plus 1 takes two values, -1 and +1. So moving to the left or moving to the right. And we can describe the history of realizations of this random variable as follows. Wavy brackets sigma t is equal to a tuple of realizations of the random variable. Now this could be seen as a tuple or a list of events or realizations. In fact, the order, as you will notice, doesn't really matter, so we could view this as a list from a Pythonian perspective. Initial conditions at t is equal to 0 apply. It is plausible to assume that initially we are at 0, but of course you can put the random walker wherever you wish. And as there is no prior history, we select the random variable as follows. Sigma 1 is plus 1, so a right move with probability q, and sigma 1 is equal to minus 1, a left move with probability 1 minus q. Once time progresses, a history, a path emerges, and we select a time k at random from all prior points in time. Every point is equally likely. After selecting time k, we take the random variable using the following process. Sigma t plus 1 is equal to sigma k with probability p, so that is persistence, and the alternative is that sigma t plus 1 is equal to minus sigma k with probability 1 minus p. Now this sounds rather complicated. Hence it is useful to write a Python script to simulate this process. Again, I stress that all the codes are available on GitHub. The link is down below in the description. If you have any questions, please leave a comment. I define the parameters of my problem. This includes the initial position, which I just put at 0. The first move to the right, where I put a probability of q is equal to 0.5, and the number of steps. So this basically tells me how many times I actually want to run this process. I put it at 1000. When I implement the stochastic evolution equation, I specify the position array, basically an empty shell with the correct dimensions. I use the numpy zeros, so it's just an all-zero array or vector. I add the initial position using indexing. Then I create an array of random realizations in the range 0 to 1, so I use here the random rand function. Now we use that to simply obtain probabilities, and you will see that in the if statement in a minute. Finally, I start the history, which is initially just an empty shell, so it's just open closed rectangular brackets. The first step can be written as follows using the if-else statement you see. I look at my random realization R, I take the one in position 1 and compare this to my probability q, so that's the first move probability. And if I am at the 50% mark or below, I move to the right, otherwise I move to the left. So we can just run it up to this level and see what happens. So here you see these are my random variables, and when I look at my initial position, that's the one defined here, and then I have my initial sigma, which is equal to 1. Yeah, so in this case, my random variable has a realization of 0.14, which is below 50%. So I move to the right, otherwise I would move to the left. And then I append my history. You see, initially history is just an empty list, and now I add this realization to my history. So now I throw in the 1, and so I later select from the history at random, yeah, following the rules. And then I have here my evolution, so I would update my initial position with the sigma, so that's happening right now. And again I use indexing, so when you look at the array, I start here at 0, initial condition, and then I move to 1, so I move to the right, and then of course the whole fun starts. So now what I do is I run a random choice from my history. So that is random choice. So that is exactly what we wanted it to be. So this is all equally likely. So I just pick at random one of these realizations. And then I check whether persistence applies or not. So that's my if condition here. So persistence probability in my case is quite high. I think it's 80%. So it's quite likely I'm persistent. Otherwise, I go into the negative realization, so it's minus sigma k. And again, I append the history and so on, and then I update my position. I use here the index IDX, starting from position 2, going all the way up to M capital N. And finally, I visualize it using the standard matplotlib.pyplot approach. Good, so let me just run this and see what happens. So it seems to run through, and you see indeed it looks very persistent. So it does not quite look like a standard random walk. But of course here we use a very high persistence probability. If we lower this to a 50-50, so this would be basically no persistence at all, it's just 50-50, then it will pretty much look like a standard random walk. Of course, if you have a more subtle probability around, say, 60%, you might not really notice a huge difference. You might have more, a tendency to go into a certain direction. So that's the random walk with memory. We have a nice implementation now in Python. This is really useful if you want to explore this further and discuss certain properties and so on. You want to check the equations you find in the papers. If you like this content, please like and subscribe, share the joy of data analysis, and I see you in the next one.